Okay, we're back on. We're starting the second half of the workshop now. Cool.
Oh.
Okay, so just before the break, we finished up with this obscure function called the Riemann zeta function, and I mentioned something about complex numbers, or imaginary numbers. So the next part of this session, we're going to talk a bit more about these complex numbers. Yeah, so to clarify, mathematicians use the words imaginary and complex interchangeably, and they both mean the same thing. Imaginary number is a complex number.
I thought they are different.
No, same thing. It's just that imaginary is a bit of an insult to the numbers because a lot of mathematicians don't think they're real. So basically, the premise of a complex number is mathematicians ask the question, what happens if you take the square root of -1? So what this question means is, if you think about square roots of things, like square root of 4 is equal to 2, because 2 times 2 is equal to 4, or the square root of 9 is equal to 3, because 3 times 3 is equal to 9. So that's square roots. But what happens if you look at the square root of -1? Does anyone know what that's equal to?
I know.
Yeah, basically there is no answer to this question. Okay, so that's not what he meant. I is the correct answer, but it's the letter used to represent this construct. You can't really take the square root of a negative number. Well, my eye is ugly.
Yes.
Okay. Okay, here's the superior eye.
Okay, that's it.
Okay, this is I. So you can't take the... No, J is more like this. Okay, never mind. So square root of negative numbers is not a thing because basically what a square root is, or squaring is multiplying two numbers together. So 3 squared is 3 times 3 equal to 9. And when you multiply negative numbers together, like say -3 times -3, that makes a positive number. So square rooting negative numbers doesn't make a lot of sense in the real number plane.
Hey, but because I have one thought about how we actually, why we have these rules when we multiply negative numbers, why they give us a plus.
Do you have a theory for that?
Yeah. What is the theory for this?
I don't know how to explain it exactly. I think when you have a negative number, say here, -3, multiplication is equivalent to addition, adding that back on to the number plane.
Mm-hmm.
So -3 times put you back up here. That makes sense. Don't know exactly how to describe that.
But negative.
Yeah, it's a bit counterintuitive.
Yeah, like -3 3 times is 0. It's 6.
Well, it's kind of like more like a rotation. Maybe don't think of it exactly.
If you just 3 times, you put it like -3, it's 0.
Okay, not so much an addition.
But this way you are doing 3 times, not -3.
Not so much an addition, but a multiplication. I'll answer this question later because it's not. Is that okay? Because it's not directly related to the talk.
Okay,
cool.
Sorry.
We can talk about some weird things that contradict themselves later because it's sometimes hard to explain. But back to the square root of -1 thing. So if you take the square root of a negative number, it doesn't make a lot of sense. So mathematicians call this number I, and that is a complex or imaginary number. So I hope I understand this a bit better. I'm going to ask the following question. Out of these 4 numbers, which of these do you believe exists? And there's no right or wrong answer, so you can think about it any way you like. So for example, does everyone here think the number 2 exists? Is 2 real?
Yes.
Yes? And why is that?
Why is that?
I know I'm putting you on the spot here, you don't have to answer this, but...
I think number is a concept.
Well,
it exists as a concept or as a unity.
You can think of a concept. You can think of counting as a concept. If you think of number 2, you can have like 2 pens or 2 objects, for example. With the square root of 2, that's something like 1.4 something, I'm not sure.
It belongs to the real ensemble.
It belongs to the real number line. So if you think of numbers as a line, like this, is 0,
yes.
1, 2. Square root of 2 is probably somewhere here. So you can think of that in terms of numbers. Square root of -1
It cannot
is,
be put in the line, so it's
we don't know where to put that because it doesn't really have like, is it here, is it here, is it here? It doesn't make a lot of sense. Actually, how mathematicians resolve that is we call this the real number line. So these are the real numbers. And then we draw another line perpendicular to this. And we call them the imaginary numbers.
yeah.
And we believe that this weird I, so I is equal to square root of -1 thing, exists somewhere out here perpendicular to that. So it's often one reason why mathematicians don't really think this is real. We can't really put this thing on a line because it doesn't evaluate to any number. We can evaluate the square root of 2, but we can't calculate what this thing is. It's more like a concept. It's not really an actual number. Same with something like infinity. Infinity is also more of a concept. We can't really define a number infinity, but we can define it as a construct. If you keep making numbers larger and larger and larger, we'll approach this thing called infinity. So in mathematics, everything doesn't always have to be something that exists. It can be something more abstract as well and just a construct. So that's really the point of the complex numbers. So as far as complex numbers are concerned, you don't have to believe that the number is real, but you can maybe convince yourself that in some imaginary universe, different to the numbers we think of as the counting system, there's something out there that if we define as I squared equal to -1, then I is the square root of -1. And what mathematicians do, they just assume this is true. And by assuming this statement is true, they're able to discover a lot more mathematics. And this mathematics has found a lot of applications in the real world, in engineering, physics, and other disciplines. So this is really the point of complex numbers. So I think I've shown this briefly, but complex numbers are represented as sum of a real and imaginary number. So on this plane. So I'll redraw this to make it a bit simpler. Yep. So this is our real number line. This is our imaginary number line. And like in a normal number line, we can draw the numbers on here. And this extends out either way. And in imaginary plane, we have I, 2i, 3i, and similarly we have negative i's. And that also goes on forever, either way. And so we can think of this imaginary plane as somewhere perpendicular to the real one. So if you think of all the real numbers you know, counting from 1, 2, 3 off to infinity, all the decimals as well, there's also this larger, bigger number system that exists somewhere where all these imaginary numbers are defined. And so if we want to represent an imaginary number, for example, this one here would be 2 plus 2i. So everything in this bigger number system of complex numbers is some combination of a real number, 2, plus an imaginary 2i. Similarly, this number down here is like -2 plus I. So it's a bit like a coordinate system, but in a different dimension. And so where complex numbers get a bit more confusing to understand is when you think about multiplication or division in this number system. So in complex numbers, multiplication is thought of as being like a rotation around the number plane. So if we look at ordinary multiplication, just in the usual system, if you want to multiply 2 times 1, that's just equal to 2, right? If you look at 2 here in the real number line and multiply it by 1, it's almost like a full rotation. It comes back to where it is, because when you multiply anything by 1, it's itself. So you can kind of abstract the way you're used to thinking about multiplication and think about it more instead in terms of this visual rotations. So multiplying something by 1 is like a full circle coming back to itself. Multiplying something by -1 transforms it into the negative plane, or if it's negative, it transforms it back into the positive plane. So for example, multiplying 2 by -1 is -2. And so we can think of this as rotating this 180 degrees across the axis. So I think that kind of comes back to your question before, Jago, of why negative numbers go back into the positive plane. Mathematicians often think about it in terms of these rotations around a plane. And so if you have -2 times it by -1, it comes back to this positive plane like this. It's a bit
Interesting
bit confusing.
way of saying it.
It is. It's a bit different. It's very different probably to how we ever learnt it in school or uni. But the reason we think about it in this way is it helps us understand what happens if you want to multiply imaginary numbers. So these are like numbers we're used to, multiplying something by 1 or -1. But what we're not so used to is what happens if we multiply something by I, this imaginary thing. So multiplication by I is equivalent to 90-degree rotations around the number plane. So what happens is the size of the number is preserved. So a 2 is still a 2, but when you multiply it by I, it goes 90 degrees and becomes 2i. So 2 times I is 2i. Likewise, 2i times I is another 90 degrees, and it goes to -2. So 2i times I is -2. -2 times I is -2i, and starting from -2i times I is another rotation back to 2. So it's like a trick. If you want to understand how to multiply these numbers together, you can think of it in terms of a rotation around a plane. So for example, so do another one, -3i times I. We have our real plane, our imaginary plane. -3i is somewhere down here. If you multiply by I, it's like a rotation back to +3. So -i times I is equal to 3. That kind of makes sense how that works. Like if I gave a
It does.
multiplication, yeah, okay. So basically just think multiply by I, we're rotating around the plane. So what's interesting is
It doesn't make sense at all.
doesn't make sense. What part doesn't make sense?
Because if I see read it 2i per I, how can be an imaginary number become a real number?
Yeah, that's a good question. So if we have this one here, so -3i times I, and remember that I is equal to the square root of -1. And there's this rule in mathematics, so when you multiply two square roots together, it's equal to the original thing under the square root. So this. So that's one of the rules of.
So this imaginary number is always like a -1.
Yeah,
not another one.
It's a square root of -1.
Okay.
So you can kind of think of it that sometimes it's in this imaginary plane, but you can do some operations that bring it back into the real number plane. So this one here simplifies to this, and because I squared is equivalent to this, it's similar to -3 times -1, which we can do as a real operation, and it's 3. So even though it starts off with this imaginary number, because of this operation here, it comes back into the real number line. Hopefully that helps explain it. Okay, so let's move on. So yeah.
Sorry. So like how you say it now, mathematician just invented to put it there.
Yeah.
There is, they don't know where to put it, so they put it just vertical.
Yeah, basically they invented it. It doesn't make a lot of sense, so it's a construct that's been invented by mathematicians.
And the physicians
Okay, they just
use it. So,
create.
Yeah, physicists.
so it does make sense after all.
Yeah, well, it doesn't make sense, but then at the same time it does make sense because it has a lot of applications.
So,
Yeah.
Which kind of applications, for example, or at least one, you know?
We'll get to it later, but some
okay.
things are like to do with encryption and that type of stuff. So a lot of computer science type applications.
Electricity and physics as well.
Yeah, electricity and physics, particle physics, various things.
What is this?
So what this is this is this is a real complex plane again. So this is our real number line. This is our imaginary number line. But now we've drawn a whole grid across this plane. And what you should watch as this rotation occurs is we have this number here, I, and we're multiplying it by itself, and you can watch the circle rotate across the plane as it happens. So when I was talking about the rotations, this illustration illustrates if we multiply everything by itself under this squared function. for example, if we take 2i by 2i, and this animation is illustrating where this will go. So if you follow this one here, for example, it comes out to -4. 2i times 2i is -4.
But you destroy by this operation the space. You should not do it.
You should not do that. So yeah, this is basically an illustration of what happens when you multiply things in a complex plane. It's all a series of rotations. So that's a very quick introduction to complex numbers, but the reason we did that is to now understand this Riemann hypothesis, which has a lot to do with complex numbers. So back to this strange function from before. We remember this is like adding up, if I find my thing where I wrote it down last time. This function here is like adding up the sum of lots of these 1 over n to the power of s things, but you can vary which value of s you want to put in here. Or you can make s a real number like 2, or you can also make s an imaginary number like 2i. And so this is a bit abstract, but let's go into what this has to do with this Riemann hypothesis thing. So Riemann hypothesis is not going to make sense straight away, but the statement is the real part of every non-trivial zero of the Riemann zeta function is a half. You can take a moment to read that, but it's basically a bunch of like gobbledygook. So we'll get back to that. Basically, keep that in mind that.
Wait, what's the real part of every non-trivial zero?
So keeping in mind the Riemann zeta function is this thing. Non-trivial.
You should say, of course, yes.
Mathematicians love to use this word trivial. To them, it means things that are obvious to them, even though it's not obvious to anyone else who's not a mathematician.
In that case, what does it mean?
Non-trivial, well, we'll get to it. Yeah, zero can be non-trivial. It doesn't make a lot of sense.
No, it doesn't.
It doesn't. Okay, but by the end of this talk, you'll understand what it means.
Yes.
We're building up to it.
Okay, now I'm hooked.
That's okay.
I was hooked, but I'm even.
So the more basic version is this weird statement of this Riemann hypothesis that sounds very obscure. It tells us something about the distribution of prime numbers.
Most definitely.
So what? So remember, the prime numbers are these things, and the distribution means what would come next in this pattern and why. And no mathematician to this point has been able to answer this question. But the mathematician Riemann, back in the 1800s, wrote this very famous 8-page paper where he was able to prove lots of really interesting results about prime numbers and this Riemann zeta function. And still to this day, a lot of the things he conjectured in this paper are still not fully understood by mathematicians, but it is believed that if we can fully understand everything he wrote in this paper, we'll have a really deep understanding of the prime numbers. So back to the zeta function. In the real number line, this function often evaluates to very nice things. So zeta 2 is equal to pi squared over 6. So we can take a look at why this is the case, and this will help us also better understand what happens when you put imaginary numbers into this S. So if we look at zeta 2, so remember the Riemann zeta function is this one here. But S in this case instead of...
What is the sum?
So sum...
Yeah.
Oh, is there wrong?
Yeah, like we could mention.
Yeah, so the sum is just adding up each of these.
What?
All children like me. Oh.
Yeah, so the sum is just starting from 1 and adding up like 2 plus 3 plus 4 plus 5 and so on.
Oh, no.
And so we just use...
Mentioning what will sum this, this sum will do.
Okay.
Oh, okay. We'll get to that. So this is just how you expand this thing. This symbol here is just a shorthand notation for this larger thing here, because it's much more concise to write it like this instead of like this, because this one goes on forever.
Somewhere.
So there's some...
So it goes to infinity and...
There's some nice relationship that this is actually equal to pi squared over 6. To understand that, we can think of the number line. So this first one here, 1 over 1 squared, is just equal to 1. I'll do this in a different color so I can actually see it. So it's equal to 1. 1 over 2 squared is 1 over 4, because 2 squared is 4. 1 over 3 squared is 1 over 9. 1 over 4 squared is 1 over 16, and so on. You'll notice that each of these numbers in the series gets smaller and smaller and smaller. So this is actually just a sum of things that get smaller each time. So if we have a number line, 0, number 1, So that's the first one. That's 1. The next one is 1/4. Next one is 1/9, which is smaller than 1/4. 1/16, which is smaller, and so on. And we keep adding these together, and they get smaller and smaller each time to the point that they kind of hit this number here. And this turns out to be pi squared 1/6. So that's basically how the sum works, and it also works out to nice numbers like this for lots of other values of s that are in the real number line. So with my animations here.
It's an assumption or the real thing?
It's very much real. So
It's true.
yeah, because we know we can evaluate these numbers. There's nothing weird about these numbers. So what this animation is showing is this part is 1, this is 1/4, this is 1/9. And we keep adding numbers that get smaller and smaller. And if we keep doing this up into infinity, these numbers get so small that it's almost like adding 0. And so the sum eventually reaches this number here, which is the pi squared on 6. And this happens for a lot of real numbers. What happens? Sorry.
It's like Achilles and torture, you know? It will overcome then, no? If it's so small, but it's still existent.
It tends to, in the limit to infinity, it becomes 0. You can think of it, it's not exactly 0, but you can think of it as converging to 0.
Here it's 2, you have the square, but if you don't have the square, then it doesn't converge, and it's...
Yeah, that's right, yeah.
I think that's what you were saying.
Yeah, so in mathematics, we can say a series is convergent or divergent. If it diverges, it goes off to something like infinity. If we say it converges, it looks like it's becoming smaller and smaller till it eventually reaches some point. And in this case, it reaches this one here.
So Zeno, it's...
Yeah. So what happens when you put in some negative numbers? This sum starts behaving in a strange way.
Sorry, I'm interrupting. Why there is P?
Where's P?
He needs the proofs that this result. He doesn't understand.
Well, which part don't you understand?
The previous screen.
This one?
Yes. He needs a proof of it.
Which part?
The P square.
Oh, the pi? So
it's a pi.
So this number is just...
what is this pi? It's a...
3.14.
Yeah?
Yeah.
This one?
3.14 squared
Why?
over 6.
Where is this relation? Why it's pi?
That will take probably another hour to explain. I'll send you a video afterwards. There's actually a really good video on this.
Okay.
Yeah.
You could share about it
Yeah.
after this video. Like
It's got to
what
do
is
with,
pi and-
because pi's got to do with circles, right? And it's got to do with like
Yeah,
circles.
it's with circle. So it's like, and zeta is
It's just a symbol.
just a symbol what represents this function.
Represents this function, yeah. This
Okay.
relationship here. Yeah.
So it's nothing with imaginary numbers yet.
Not yet.
Okay.
Not yet, but almost. So this again is not an imaginary number, just a normal negative number. But this function starts doing weird things when you put negative numbers in. So zeta function, when we have s is equal to -1, is equal to 1 over -1 to -1. Oops, that should be a plus. 3 -1, 4 -1, and so on. What happens in this case? 1 divided by 1 to the power of -1 is equal to 1. This is equal to 2. This is equal to 3 and 4 and to infinity. So just looking at this sum gets larger and larger and larger. We keep adding larger numbers to it. So we can think that it goes off somewhere to infinity because it just becomes larger. But interesting enough, mathematicians believe that this is the case, that it's equal to -1 over 12. And it seems like one of the most counterintuitive things ever, because how can something where you're adding larger and larger things come to a fixed number? That's part of the Riemann hypothesis. So that's one of the weird mysteries. And also same with this one here. It also becomes larger and larger in the same way as this one, but mathematicians believe it goes to 0. So there's some really counterintuitive results, and this is where we have to start bringing the complex numbers into it to understand these. To understand this, Riemann asked what happens if the s in the zeta function is a complex number. So for example, in the function, let's put 2 plus I, where I is imaginary. So to understand this, back over here. Oh, no, screen. Zeta 2 plus I. And the function is 1 over n to the power of 2 plus I. And if we expand this, then n is 1. And again, we keep summing up to infinity again. And what is strange this time is because we have this imaginary number in the exponent, it makes it quite hard to evaluate this using the normal rules we would use for mathematics. So how do we do this? First thing is to remember what I said about complex numbers being about rotations in the number plane. So if we look at an exponent like a half, raise it to the power of 2 plus I. There's this rule that you may have seen in school where you can represent an exponential exponent of things added together as multiplication. So what I mean by that is 2 to the power of 2 plus 4 can be written as 2 to the power 2 times 2 to the power 4. You can do the exact same thing in complex numbers. So it's equivalent to a half to the power of 2 times half to the power of I. So that's one of the ways you can start to reduce the complexity of this. And we know that this thing here is constant. That's just equal to a quarter. And what happens in complex numbers, this part here is multiplying by a complex number. This is complex. It doesn't matter too much exactly what a half to the power of I is. But what does matter is its multiplication by a complex number. So what ends up happening is this thing here evaluates to a quarter times some rotation in the plane. So the final thing is the length of a quarter, but rotated somewhere. So in our plane, real, imaginary, you can have a quarter here. And the effect of multiplying by this half to the power of I is like rotating it in some direction to some degree. So even though this looks quite scary, you can just understand it as there's something in the real number plane that is like the length of it, and this imaginary thing is just like rotating it by some degree. I think I might have an animation for this as well. Yeah, so if we think about this whole zeta function, we remember from the previous one that zeta 2 is equal to this pi squared over 6 number, like 2 point something here. But if we add the zeta 2 plus I, it's still the same length, it's still here, but it's just being rotated by some amount. So each of these terms you can think of being rotated to some degree across the plane because of the effect of this I thing, and the answer ends up being somewhere out here. We don't have to worry too much about the exact numbers here, but it's just basically the concept of the effect of a complex number is to cause some rotation. And the important thing is the length of this line is still the same as it was when it was zeta 2. So that's, I guess, some understanding of the weird stuff that happens with the complex numbers. But then what happens after that? So this example here was 2 plus I, but we can keep putting in different values of s in the complex plane. And we see mathematicians did this for a lot of values of s in this half of the plane. The things work out to evaluate to quite nice numbers that we can plot like this. So this region here, going a bit too forward, when we evaluate this function for any of the numbers in this side of the complex plane, this is basically an animation of if we took all the things on this grid line and plugged them into this function, what would we get? This is the resulting picture of what happens under this function. So it works out quite nicely, and the pattern itself looks really beautiful. But what happens over here, we get these really counterintuitive things I showed before. Like if we plug in -1, we get something like this, where it looks like it's going off into infinity. And we can't really plot infinity on this grid. Infinity is like somewhere way out there. So what mathematicians try to understand, and when they reach the point of understanding that for these numbers in this side of the plane, this really pretty pattern occurs, what they want to understand is what happens like this. Wouldn't it just make sense to extend it and make the whole pattern look like this. So have I lost anyone? Is everyone kind of following the gist of this?
It's complex, yes.
It is complex.
It's complex numbers.
I don't understand what this animation is about.
So what it is, so if we go back to, so you're okay with this part, that the zeta 2 is equal to pi on 6. When we do zeta 2 plus I, it's like rotating this number.
Okay.
We plug in any other value of s in the complex plane. We can do zeta 3 plus I, zeta, I don't know, 2 minus I, and we can evaluate those numbers. And so what this animation is, it's showing the zeta s for any of the numbers in this grid. It's basically plotting the function.
It mentions me already not just a number, but like a behavior of some kind of object, you know, on plane.
Kind
It's
of.
not just a number, it's already object. It's like
Like an object.
Like object behavior. This eye makes it behaving like in weird way.
It is, yeah. It's doing weird stuff to
seems
it.
like a magnetic
Yes.
field.
Kind of.
Yeah, it seems like.
I mean, because if you
Yeah.
look at other functions, I mean, if you said to someone, plot like a parabola, y equals x squared, I mean, you've probably seen this kind of thing from school where it looks like that. We're really doing the same thing here, but we're doing it in a different number plane.
It's really interesting to get this animation because when I went to school, it was always, so we had only one example of function.
Yeah.
So now it's like I get something new.
Yeah, I found this on some YouTube video and I stole his animations because I really like the way he portrayed it like this. It makes it a lot easier to understand. So basically, mathematicians evaluated this, but this function is not well defined in this plane. But what they want to pretend to assume is what happens if we just assume this is well defined and it completes the pattern, so it looks as pretty as this. And this is basically what the Riemann hypothesis is, trying to prove that this is true. Like, we already know that this part is true, but Riemann hypothesis is proving our belief that we can just assume that the rest of the function in the complex plane also looks as pretty as this.
Symmetric.
Yeah. So that leads us into the,
It's always the case, symmetry.
that's what they want to prove. That's what mathematicians believe, but no one's really proven it yet, why exactly it is the case. One reason why they believe it is if you think about, okay, let's assume it isn't symmetric, it's something else. What is this function? It could be some other variation. A trick that mathematicians like to use is the concept of being differentiable at a point. And they call this an analytic function, so when a function is differentiable all throughout. And in mathematics, you represent this as preserving angles in the function. So in this animation, this is not a Riemann complex function, this is just a regular function, s squared, so squaring a number. And they've just taken a random angle here. So if we go back to the start of the animation, angle between these two lines is 67 degrees, like measured on a protractor. And then when you apply this function, s squared, they've bent the lines with the function and the angle is still 67 degrees. This is called an angle preserving function. It doesn't happen with all functions, but in a special class of functions called the analytic functions, sometimes they preserve the angles. And so with the Riemann function, if you impose this restriction that the function is differentiable everywhere, that the angles are preserved, then your only possible solution is the symmetrical function. So that's what mathematicians believe is the solution here. But the million-dollar question is proving exactly why is this the case? Why should it be symmetrical? We believe that under certain conditions it should be, but actually writing down the formal logical proof and working out every single, I guess, detail of this proof is the million-dollar question that still has been unsolved. So back to...
I know the answer.
Do you?
It's the answer is that's positive numbers and negative numbers. It's just miracle, or not miracle, but mirror. Excuse me. Miracle also.
It's just a miracle. That's your
It's just a
proof.
miracle. That's it. that's
Magic.
That's a magic.
You can have $1 million for that. Yeah.
I will answer like this.
Who does he call? Where's the phone number?
Yeah, there's like some organization you got to contact or something. So if we go back here a bit, the actual statement of the hypothesis is a bit more obscure. This real part of every non-trivial zero of the Riemann zeta function is a half. So we'll now explain what this actually means. because it's not as concise as the function is symmetrical. So basically, the Riemann hypothesis is about where the zeros occur in a function. So if you think about a function like, I don't know, y equals x plus 3, we can plot this in like a real number line, and it looks something like a line, right? And you can think of where is the 0 in this function? Well, the 0 is at 3. It's a similar type of thing in the zeta function. We want to know where is this function equal to 0? So where is zeta s equal to 0? And what Riemann hypothesized is that all the zeros lie in this area here. She calls the critical strip. So we can look at another animation to help understand this. So this one here. So if you follow any of these dots as the animation runs, you can see they're all pulled into the origin, go into 0. So for example, so this is the zeta function again. So zeta negative 2 is equal to 0. So this is true. And similarly, zeta negative 4 is equal to 0. And negative 6, negative 8, and so on. So if you see the pattern here, it's all the negative even integers. This is what that non-trivial 0 phrase in the statement meant. The trivial zeros are these ones, because they're kind of like obvious. They're like the obvious zeros. So.
And someone has proved it, or is it just what we see?
This part I think has, well, yeah, this has been proved because it's a part that's trivial. It's obvious. But what isn't so obvious is what other things in this plane come into 0 as well. As looking at this animation, we can see the yellow circles fall into 0. It looks like they're kind of falling into the origin. But there's also a whole bunch of other numbers somewhere along this critical plane here that also come into 0. And what hasn't been proven is exactly what those other numbers are. And that's why they've defined this critical strip here, because somewhere in here, this is what the question marks are, there's a whole bunch of numbers that also map to 0 under this function. And that's what the Riemann hypothesis is about, the non-trivial zeros. And the hypothesis is that all these other things that go to 0 all lie on this line here. So this is a half. So this is 0, 1, and the half line is here. And Riemann hypothesized that in the real number plane, that they lie somewhere here. But knowing exactly what those numbers are is the unsolved question. An interesting part is that this distribution of where these numbers occur encodes the distribution of the prime numbers themselves. Not directly, it's not the actual prime numbers, but it's been used to prove where prime numbers can exist, the distribution as prime numbers get larger and larger, where they may occur. So, you know, I guess no intuitive way, because it doesn't appear clear at first what this has to do with the prime numbers, but if this function can be solved, it will help us better understand like where the prime numbers are. And help us answer this obscure question of when we have prime numbers, which one comes next and why.
How old is this question?
From 1850s, I think.
1850.
Yeah. It's Riemann, 1859. So yeah, many people have attempted it and still haven't solved, and they have failed big time.
And you think you will succeed.
We don't recommend to do that as a PhD topic.
I think mathematicians joke that it's the hardest way to win $1 million. Because if you solve this, you can win $1 million, but it's like there's far easier ways. This is just too hard.
But I remember a few years ago, there was one question like this, and some mathematician solved the trouble, and he got money. So.
Yes, yeah, one did. Russian mathematician solved. There's actually 7 of these types of questions. One of them got solved, but the guy who solved it, he actually didn't claim the prize money. He gave it back to the institute. Just money. Yeah, that guy.
Perelman.
Yeah. Yeah, he didn't like the whole idea, so he gave the money back.
Wait, what?
Yeah, he solved the problem, and they gave him $1 million, and he's like, no, take the $1 million, I don't want it. Yeah, it's a bit crazy.
Retired in the long days,
Yes, that guy. So to finish up with, why does this whole problem matter? Well, what's it got to do with the real world? Well, it's this strange idea that if someone solves the Riemann hypothesis, it will break the internet. The reason some people believe this is that the Riemann hypothesis and prime numbers in general have a lot to do with how encryption systems work, like the encryption that makes sure when you do a bank account transaction that it's secure. And one way to... Oh, you have a question?
No, I wanted to say that people say the same about quantum computers.
Yes, yeah.
So
And actually for the same reasons. Because one of the encryption algorithms that's used, it's not used so much these days because people are trying to discover new algorithms in case someone breaks one of the previous ones. But one of the first algorithms for encryption use was this RSA algorithm. And basically, the whole premise of the algorithm is you have to start by choosing two prime numbers. And you have to choose two really, really, really large prime numbers for this thing to be secure. And then the algorithm goes, you define this number n, which you multiply your two prime numbers you chose together, and that gets you n. And then make this other number a, which you get by this formula, subtracting one from the first prime number, one from the second one, and then multiplying that together. And then there's this kind of convoluted instruction to choose an integer between 1 and your number a that you get, so that there's no common factors between e and a. And I'll get back to that in a sec, but yeah, and then there's the final step where you have to find another integer d. And so this algorithm is basically the algorithm that underlies a lot of our encryption systems. But most of the concern is that the starting point is to start with two large prime numbers. And the whole basis of the algorithm is that it's difficult to find factors of very large numbers and factor them into prime numbers. And as time has gone on, as computers have gone faster and faster, and especially the fear with quantum computers getting even faster, you'll be able to crack a lot of these codes by being able to do the computations on the prime numbers a lot faster. And so that is the fear that some people think, oh, if we crack the Riemann hypothesis, we'll fully understand how prime numbers work. And so the internet may break, or encryption systems may break as a result. So that's why there's a lot of efforts going on among researchers around the world. Like in the NSA, for example, they hire a ton of mathematicians to work on new encryption algorithms that you can't break. And so that's one of the really interesting applications of Riemann. So anyone got any other questions? Because aside from that, I think it's a good place to leave our talk today.
Yes, can you explain the RSA encryption?
Yeah, we can go through it with an actual example.
Schedules, okay. No, I don't know how to say it, whatever.
So I don't know how to show both the iPad and the thing at the same time. So we move back and forth. And basically, these are like two prime numbers you choose yourself. So we can just say, let's go with these two. In reality, for the encryption algorithm to work, you have to choose massive prime numbers, but I wouldn't be able to do the multiplication or whatever quick enough by paper. So let's just make it simple for now, just to pretend. So that's the first step, just choose prime numbers. Second step is to multiply your two choices of prime numbers together. And then we just call this thing n. So 3 times 11 is 33, and that's what we call n. And what this n is, it forms part of your public key.
Okay.
So anyone who's worked with encryption before may have heard of this private public key thing. And the same concept happens here, where you're allowed to share this number with anyone you're interacting with over the internet, but you also then have a private key, which you have to keep secure, kind of like your password. You can't share that. So next step is a equal to p minus 1, q minus 1. So p minus 1 is 2, q minus 1 is 10. So a is equal to 20. The next step is...
What is this?
That's kind of like an intermediate. It's neither public or private key. But what happens is we have to choose this number e, which is important because that's part of your public key. So e is a number that is greater than 1, but less than number a. That when you look at a, e and a share no common factors. So what I mean by that is if you have the number 6 and 4, the factors of 6 are like 3 and 2, or like 1 and 6. Factors of 4 are 2 and 1 and 4. These are numbers you multiply to get these numbers. So 6, 3 times 2 is 6. You can do this for any number. You can find the factors of the number. So the condition that E has to satisfy is there's no factors shared with the number A. So A is 20, and the factors of 20 are the things that multiply together to make 20. So for example, 4, 5, 10, 2, 1, 20, and so on. So these are the factors, and the E number we choose can't share any factors with 20, so it can't have any of these factors. So let's make this quicker, see what my answer says. I think E equal to 7 is one choice that works. It satisfies this constraint. So it's larger than 1, it's smaller than A, which is 20, but because 7 is a prime number, it doesn't share any of these factors. You can't multiply these things together and make 7. And the final step is to choose another integer D, and this is your private key, like your password you have to keep secure when you do the encryption.
So this intermediate step is to blurry, to make it difficult to reverse?
Yes, to reverse the encryption, yeah.
Yeah, sure.
So D is the private key. And this number also has a rule that D times E minus 1 has to be a multiple of A, and A is equal to 20. And we know that D is equal to 7, so 7D minus 1 has to be a multiple of 20. And so I'll just pick a number and show what this means. If we pick D is equal to 3, 7 times 3 minus 1 is equal to 20, which is obviously a multiple of 20 because it's 20 itself. Other multiples of 20 would be like 40, 60, 80, because you multiply it together.
Which was the computer?
Yeah, the computer, the algorithm will choose all these numbers, so we'll choose values of E, D. What happens is there's a random number generator that randomly generates 2 large prime numbers. And so one of the, vulnerabilities of the RSA algorithm is that it's reliant on this random number generator to generate really strong prime numbers that you can't decode and break. So if you decode the random number generator itself, then you can break the whole encryption. So that's why it's considered not very safe. And basically what happens is the numbers, so D is equal to 3. That's your private key. Oops, you have to keep that secure. A doesn't matter so much. But the N, this one up here, originally is equal to 33. And the E is equal to, I think, 7. So these ones you can share with anyone on the internet. That's your public key. This one you have to guard to yourself. Then what happens if you want to send an encryption over the internet, like an encrypted message? My slides are broken. So let's just think of a message. In the encryption algorithm, your message has to be encoded as numbers, so the message has to be in a number, but it could be something like, hello, and you assign each of these letters a number, like H is 5 and E is 3 or something. And just for simplicity, we can just choose like a really simple message, like M is equal to 2 or something like that. And what happens under the algorithm, we use these numbers here to encode the message. And then what happens, other way around. Someone exchanges their public key with you, and you use their public key. So you want to send someone this message. You take their public key, because that's public on the internet, and you encode the message by doing some multiplication operations using that. And then what happens, the message gets transmitted to them, they receive it, and then they decrypt it using their private key. And because of the way by which the algorithm is constructed, they'll be able to get back out this original message by doing that. And so that's basically how the exchange takes place over the internet.
What? So 33 is public key, 7
is also a public part of the public key.
Wait, what? So D is secret.
That's your secret. And you
So
use
there are
that.
two public keys, I don't get it.
Mm-hmm.
Public key consists of 2 parts.
There's 2 parts to it. Even though the thing in the computer looks a bit different, but that's because they bundle it together. But yeah, there's 2 parts to the public key.
And you send both?
You make them public.
We make them public. So anyone can see this, but you have to guard this because it's secret.
And you can sign also this way.
Yep.
Using the
You
private
can
key.
do SSL certificate, that kind of thing.
It's presented as one single string.
Yep.
But
But
the
it's actually-
string is actually composed of two. Okay. I don't
Well, that's under RSA. Under other encryption systems, it could be composed of even more numbers. There's lots of other algorithms.
I
Yeah.
understand how it works, but I wonder how is it possible to create something that quantum computer cannot break?
That cannot break.
Yes. What kind of algorithm?
Something more complex than this one.
Yes, because this one you can try everything and you
Yep.
can find the solution.
You can just keep plugging in different things, and as the computer gets faster, it can just.
What
yeah.
kind of algorithms? You cannot try everything. I don't understand.
I guess that's what all the mathematicians employed at the NSA are supposed to be figuring out right now.
But
Or you
computer
can
can
avoid
try
it.
everything anyway.
You can avoid computers altogether. If you use quantum communication, you have two atoms on the same frequency and nothing in between. So
Yes.
if the communication occurs through teleportation, there's nothing in between, nothing to intercept, so you don't need encryption at all. So there are many ways of avoiding
Yeah, I mean, maybe-
the application.
Maybe in the end, the answer is the encryption becomes.
Yes, but
So easy to break
it's
the-
not,
Yes, it's not computer, it's not math, it's
Yes, my question was about math.
But
Yeah, I guess that question hasn't really been solved yet, to be honest. There are.
another belief
Because some companies they claim they found solution
all that
for it.
bullshit.
They claim. I guess the truth will be one day when we have the quantum computer.
Working on it. It's not a company. It's a French institute. The name is CEA. And
Already?
yes, last year already
I didn't know
they are working on
Yeah, there's a lot of physicists and mathematicians working on a branch of cryptography called quantum-safe encryption algorithms, and so they're trying to find an algorithm. I think some people have claimed they have found it. I'm not exactly sure how those work, to be honest. I haven't read too much into their work, but there's definitely a lot of mathematicians around the world working on algorithms that one day when computers do become faster, we crack quantum computing, there has to be encryption algorithms that we can't crack as simply as this. But for now, these algorithms still work okay with our current computer system, but one day they won't. So yeah. Any other questions? I think
So far, so good.
it's 5:30, so I think we should probably wrap up. I think we've been here for long enough today, unless there's any other things anyone wants to discuss.
Not for only 1 year, I suppose.
Cool.
Thank you.
Thank you.
No worries.
Thank you. Wait, now Evelyn will come.
We have a test.
Yeah, we have tests for you exam.
No exams. I don't do that here.
Guys who are please don't leave.
No.
Actually, guys, who is ready to maybe to share some thoughts? You can
On camera.
speak tired with my camera. Yeah, like just
Interesting.
yeah. If you are interested, you can share your thoughts. Yeah, we have small gift for our
Oh,
T-shirt today. So
doesn't have to. Oh, thank you so much.
Thank you. That's some berries and honey
Oh.
for your immune system.
Oh, thank you. That's so cute. Thank you, Evelyn.
Have you finished?
Yeah.
Are you still alive?
yes, that's
Yes.
a lot of input. Half
Wait.
of the things I didn't understand, but
I think everyone's minds are exploding at this point.
The more you learn, the more you know. Bye.
thank you. Bye. Yes. So, what's also the side?
Yeah, you should do it.
You just